With this next video, we're going to look into what are called the quadric surfaces.
Hot stuff coming up.
I know. I agree. I am so glad.
I'm so ready.
I'm glad you're ready. And these are the 3D equivalent of the conic sections. And I might ask you to review, what do we mean when we say conic sections in pre-calculus or in calculus 2? The conic sections, why, that would be ellipses. Circles are a type of ellipse. Parabolas and hyperbolas, right? 3 different kinds of conic sections. And there are more if you start counting into the degenerate conics, but don't worry too much about that. But you know, if you think about it in 2-dimensional space, if you kick out this term and all the terms that have z's in them, like this one and this one and this one, you would have a conic section. But now we're in 3-dimensional space, so we're going to have something more interesting than that. We're going to have a quadric surface. And there are 6 basic types. Ellipsoid, and you can probably guess, oh, I bet that's like an ellipse, only solid. Okay, now this might boggle your mind. A hyperboloid of 1 sheet, a hyperboloid of 2 sheets, an elliptic cone, an elliptic paraboloid, and a hyperbolic paraboloid. And the names are, as you know, if you were to say parabola, ellipse, hyperbola, look how much those words are showing up here. So the names are even similar to the conics, and they do have to do with the trace of each surface and each of the coordinate planes. Remember how to find the trace in the xy plane, let z be 0. To find the trace in the yz plane, let x be 0, etc. So my software doesn't draw them. The problem is you wind up with complex numbers, with imaginary numbers, and they can't be shown in the domain. And as soon as you wind up with some imaginary number as part of the domain, it just won't graph. I wish the software would graph and just leave blank any places that's not in the domain, but unfortunately I can't get it to do that. Sometimes I can trick it into graphing things, but not the quadric surfaces. For example, like if you solve this for z, you get z equals the square root. Actually, you get z equals c squared times the square root of 1 minus x squared over a squared plus y squared over b squared. Well, you know, the problem with that is for x's and y's, a lot of x's and y's, that turns out to be a negative number under a radical, so you get imaginaries, and it won't graph. Anything that has in a domain, anything where there's an imaginary number as the range value, my software says no thanks, can't do that. So here is a picture of an ellipsoid, and you can kind of see, you know, in the xy plane when z is 0. See, here's the xy plane. When z is 0, it forms this ellipse, right? In the xy plane. I'm thinking of this as the x-axis, and maybe I should do it here. This is the x-axis, and this is the y-axis, so it forms this ellipse. In the xz plane, it forms an ellipse kind of shaped like these circles here. This one is, but it wouldn't have to be circular. And in the yz plane, of course, x is 0, so in the yz plane, that would be this one, right? You can see that it also forms an ellipse. So hence the word ellipsoid, because it's an ellipse in possibly all 3 coordinate planes. Its trace is an ellipse. I mean, some of them might be circles, but you know, you can't really tell that for sure, but so you put more into it. So now here's another one, a hyperboloid of 1 sheet, and I think you'll see why it's a hyperboloid of 1 sheet when we look at it. By the way, notice the traces in the xy plane. It's an ellipse. See, look here at the xy plane, it's an ellipse. Look at the yz plane, it's a hyperbola. So in the yz plane, it's a hyperbola, and there it is, you can see it. And in the xz plane also, let me see, that would be this one. No, this one, also a hyperbola, right? So in xy, it's an ellipse. In the yz and in the xz, It's a hyperbola, so hence a hyperboloid of one sheet. And the reason why it's called a one sheet, if I had an infinite piece of material, I could stretch that to be this surface. I mean, it also has to be infinitely rubbery, I guess, but I could stretch it to make this particular surface with just one sheet. And of course, since there's a hyperboloid of one sheet, but there must be a hyperboloid of two sheets. And now, before I just show it to you, let's look at it. It's very interesting. If we say, let's look at it in the xy plane, then z would be 0. And hey, it doesn't even exist. If z is 0, we have negative something squared minus something squared equal to 1. It's impossible. So in the xy plane, this doesn't exist. Now in the yz plane, make x be 0, right? Then this is a hyperbola. I think that's kind of obvious. And in the, that was the yz, and in the xz plane, kick this one out, and we also have a hyperbola. But it does not exist at all in the xy plane. Would you like to see a picture? And here it is, see? No intersection in the xy plane. In the, which one did I do first? In the yz plane, that's you know, this one right here, it's a hyperbola. See it here and down here also? Hyperbola. And in the xz plane, that would be the one this way, again, a hyperbola. And so, and now you see why it's called a hyperboloid of two sheets. If you were to try to make a surface out of this one, you would need two different rubber sheets, the upper and the lower, so to speak. So that's why it's called a hyperboloid of two sheets. And of course, again, because of the traces being hyperbolas, you can probably understand why it's called a hyperboloid. Okay, here's another one. This is kind of an obvious one. It's called an elliptic cone. And this is actually one that I can draw, which is kind of amazing, but I can actually get this one to be drawn here. Anything that looks like x squared over a squared plus y squared over b squared minus z squared over c squared equals 0. And what you could do to see the graph of this is solve it for z. And if you solved it for z, you get z equals c squared times, square root of c squared. So z equals c times the square root of x squared over a squared plus y squared over b squared. And if you think about it, in the xy plane, this would be 0, so it would be an ellipse. And in the xz plane, a degenerate hyperbola, see, because it doesn't equal 1, it equals 0. And in the yz plane, again, that degenerate hyperbola. So let's look at one. What I did with this one, I let c be 1/4 and the a be 9. Actually, a squared is 9, so a is 3 and b is 2, so b squared is 4. So, you know, and then I just kind of said, well, we're going to have two functions, the plus and also the minus, you know, positive and negative. And now I can graph both of them, and now you can see why it's called an elliptic cone. You can see the cone, the conical shape here, I hope. But I'm not honestly sure if you can, but I'm hoping that you can. I wonder if I can make equal scales. Would that help? No, that didn't help at all. I'm so sorry I even thought about that. But here we go, and you can see the cones touch in the middle, and you can see the degenerate hyperbola this way and also this way, right? And you can also see that you have ellipses, right? I mean, if I were to pass a plane like z equals 1 through there, let me see, I could probably do that. H of x, y. If I want to just pass a nice level plane through there, I guess I'd have to define that as equal to 1 or something like that. And now I think I can do this. I hope I haven't overreached my grapher's ability here. No, see? And this, let me adjust my picture a little bit for plot 3. I'll make the appearance of plot 3 I'll make it a nice pretty blue plane. And see, now you can see how this blue plane forms an ellipse. So cross sections, actually all cross sections that are parallel to the XY plane will be ellipses, because z would be 0, and well, no, z wouldn't be 0, but it would be a number, and so then we have x squared over a squared plus y squared over b squared equals some number, and of course those are ellipses then, so not a big deal. Let's just get rid of that anyway. Oh, look what happens. I got rid of my whole graph because this wasn't defined now, but now it's okay. It'll come back. All right, finally, here's an elliptic paraboloid, and z equals x squared over a squared plus y squared over z squared. In other words, f of x, y equals, and this looks like it would be an ellipse, but it's a function here, see? And what happens is the cross sections parallel to the xy plane would be ellipses. As a matter of fact, if I still have my func out like a stupid person, I deleted h of x, y defined to be 1, and so if I pop that in down here, you should see the intersection of the plane I just stuck in there and the surface. So we'll make plot 2. Oh, I kind of like that pretty. Let's go with a different one here. Don't go with a color map. Go with a hot pink. Fill surface with hot pink. I think that was the same one. So now you should see that. Oh, I did the wrong one. I did surface 1 with hot pink. That was my bad. But you can still see that the intersection, I'll put it back there, you can still see that the intersection was an ellipse. Actually, that one looked like a circle, but I don't know if the scales are equal. So that one definitely an ellipse there, see? And so this is an elliptic paraboloid. You can see why paraboloid, because parabola this way, ellipse this way. See, elliptic paraboloid. And finally, there's a hyperbolic paraboloid, and here's a sample of this one. By the way, these aren't so hard to draw with the software because no imaginary numbers, right? So here's this one. And this one's interesting because something like this, we'll look at this later to see what are called saddle points. The saddle point would be the point right here, and just I'm getting you a little ahead here, but just think about it. This saddle point is a minimum this way, but it's a maximum this way, right? It's a relative maximum this way and a relative minimum this way. Ooh, that's going to be strange, because when you look at derivatives, guess what? The derivative with respect to x and y are both 0 at this point, right? Because there's no increase in either direction, so it's horizontal. Horizontal tangent plane. Ooh, but not a minimum, not a maximum.